Okay.
So Olive will go first, and if he's ready, he can just go.
Okay.
Yes, I'm here. So for today, we will talk about challenge 0, the finite precision arithmetic errors and alternative representations. So next slide, please. At level 1, we started by exploring the physical limits of 8 bits. In integers exceeding 127 causes a wraparound to -128, which is a catastrophic error in most contexts. Transition into mini floats allows us to represent a wider range, but introduces precision tags. As seen in the graphs, the relative error stays low in the normal range, but spikes at the edges where the format underflows to 0 or overflows to infinity. Next, please.
Let me absorb this a second. Can you go? Let me absorb this a second. Can you go back one? Yeah. So here you have the x. So you have EM25, 34, and 43. The range is always 10 to the -4 to 10 to the +4, and the relative error goes to 1. Okay, to 10 to the -6. Okay. Nice. Look at the repulse. Yeah, it's very nice. Okay, go ahead.
Okay, so when summing many terms, the order really matters. If you add a tiny number to a huge one, the tiny one essentially disappears because the 8-bit mantissa can't hold both scales. Our plots show that as n increases, the mean error grows steadily. Even advanced techniques like Kahan summations struggle here because there simply aren't enough bits to track the compensation accurately.
So let me see a second here, right? So here you are doing. How do you choose the number here to sum? Which how do you choose the numbers to sum? For this ABC, how do you choose them?
Here I'm not sure because for this challenge, whole project, whole code was written by Howard.
I see. So you guys, yeah. Can somebody tell me how you choose the errors here? So of course you have some ABC, right? And yeah, can somebody explain what is on the x-axis? There is 1n. I don't know if you keep repeating the same addition. Can somebody tell me?
Wait for a minute. I check my code.
That's what happens when you use cloud code to do everything, right?
Yeah. So I choose numbers from 300 random numbers.
I see. And then because you have the full precision there, and you go to 10 to the power of 3, right? So this is, so then naive is the summation, but what is the setting here? Is this, which setting is this? Is this the mantissa plus exponent? What are the values of the mantissa and the exponent? Is there 2, 5? Okay, get it. 2, 5. Okay, so that's mantissa exponent. 2, 5, 3, 4, 4, 3. Okay, good. So in the absolute error, you see that it grows, but you don't see a big difference between the different approaches, right? The difference is they're all growing linearly. Okay, let's see the relative error, which is more indicative. Okay, so the blue is the naive 4, 3, right? The mantissa is 4, the exponent is 3. Of course, you saturate eventually, right? Because you go out of range. Very good. Then the second worst is the can 4, 3, right? So this is where you choose the order of summing them. Very good. Then, so you see that for 4, 3, this can method does worse than the naive one. So it doesn't improve. Then in the naive method, and the can method for 3, 4, everything is there. And 2, 5 as the largest error. Because here, so the number between 0 and 1, what's the support of the numbers that when you draw them randomly? Are they between 0 and 1? Are they between?
I'm not sure. I almost forgot what I'm done a week ago.
Not good, not good. You should remember. Because of course these numbers, right? They have these different settings. They have different range, right? So the maximum and the minimum number that they can represent is different. My suspicion is between 0. I suspect between 0 and 1. Yeah, let's see. Can you check?
Yes, I think it's
Mm-hmm.
0 to 1.
So because then, because you see that the 2.5, right? The 2.5 is the one that has the largest error, but that's because it also has the largest range, right? So the question is, what is the correct way of assessing the error with respect to the range? So of course, in this case, you're summing sort of small number. So you're using mostly the mantissa, right? Because the exponent, probably you don't fill in the because you have 1,000 numbers, right, between 0 and 1. So eventually you're going to go around 500. 500. So they, okay, understand. Yeah, you see my point, right? My point is that for the 2.5 is the one that has the largest support. So it's the one that can represent the largest numbers. And so one trick would have been to normalize all the supports to be between 0 and 1. And then you sum the numbers so that they average to 1. So that basically you fold back the support to be all between let's say -1 and 1. Does it make sense?
Yes.
Okay. Otherwise, it's not a fair comparison. Okay, go ahead.
Yep. So multiplication is even more volatile. With only 8 bits, you run out. Only 8 bits, you run out of exponent room very quickly. If your factors are mostly large, you hit the saturation ceiling almost immediately. If they're small, you underflow to 0. The 4-3 format handles this best due to its wider exponent range, but it pays for it with coarser precision.
Okay, let me pass this through, right? So this is the same setting. So the numbers between 0 and 1, right? And Jesus, you got 10 to the 10 error as an absolute error. Now, can you confirm what's the range of the numbers here? Because from the absolute error, you go to 10 to the power 25. So you take them larger than 1 for sure. Probably you take the between 0 and 10, I guess. Correct? Can you check the range of the numbers? And then the relative error versus n. Exactly as you said, the 4-3 is the one that has the largest exponent. Well, the largest exponent is 2.5, so it has a bad one. And then 3 and 5. Okay, good. Can you tell me just the range of your numbers? I think the range must have been. Yeah.
So I choose from 10 to the power of -3 to 3.
So you have the both negative and positive exponents. Okay. Yeah, because here you see that your error explodes. Basically, you accumulate a power of 10 for each multiplication, so it's not large. Okay, just put in these details next. Under flow associated multiplication of 4 factors less than 1 leads to 0. Very good. Saturation. If you go back to greater than 1, you meet the largest representative value. Okay, very good. Okay, go ahead.
Yep. So Our final test was the log sum exponent function. The naive way fails nearly like 100% of the time in 8-bit because power x grows too fast. However, by using mathematically equivalent stable version that subtracts the maximum value first, we prevent overflow entirely. This demonstrates that even with extremely poor hardware like 8 bits, we can achieve usable results through numerically stable algorithmic design.
And this is the fraction of trials, rate of plus and minus. So what is which operation was this? This was multiplication, right? This was still multiplication. Like which operation are you doing here?
Yes, I think it was multiplication.
And how did you choose the? Okay, so the x representation is in mantissa plus exponent, right? And then you put the 2, 5, the 3, 4, and the 4, 3. Very good. And then you look at the rate of plus and minus inf. But you see that your overflow rate is very large, right? So why do you say that it's very stable if with n submission you can only do 10 multiplication at most before you go completely?
It was more stable than another ones. So in comparison.
I mean, just go back to one. So do you have the curve of the, go back one slide. Can you go back to a previous slide? Can you go back? Yeah. No, not at the beginning, just the previous slide. So next. Like here, do you know what is the overflow, the plus and minus inf with the previous slide? Like what are you comparing? Do you have the plus and minus inf here? Like, do you have the same plot that compares the rate of plus and minus inf using the two representation or not? You understand the question, right?
Yes, but I don't think we have that plot.
Okay, so because if you say the representation is better, then you should have something to show it, right? You should have have the same plot with the two representations so that one does something, the other one doesn't. Okay, very good. Go ahead.
So here is the level 3, the alternative representations and advanced investigation. And we use the logarithmic number system and we compare the accuracy of LNS multiplication and addition against the minute float. And we can see that when the relative error is smaller than 0.01, the mini float is the count of mini float is bigger, but when it is bigger than 0.01, the LNS add is bigger. But then when it comes to the multiplication, the mini float multiplication is most of the time it's always bigger than the LNS multiplication. And so it comes to the conclusion that the LNS multiplication is advantageous for multiplication having machine learning workloads.
So here, so the relative, stay there. So here for the, can you go back? Yeah, so stay here. So which mini float representation do you pick here? How many mantissa, how much exponent?
Oh, let me check. I think it's 8-bit minute floats.
Yeah, okay, but how many in the mantissa, how many in the exponent? Like before in the previous slide, right? You have 4, 3, 3, 4, 2, 5. Which one it was? Okay, I can bet while you check, right?
Yes, I'm checking, but I can
My bet
find
Well,
is
we are using 4, 3.
4, 3, 4, 3. And so for the additive error is again like 1,000 for the relative. So for the addition, you have the summation of the number between 0 and 1, right? How many number do you sum for the addition? I'm just trying to understand, because here you fix the number of addition that you perform, right? And then you reproduce this multiple times, right? So I'm just trying to understand what is the setting of the two examples. Because the numbers, they average out at around, whatever, 0.1. So I suspect, yeah. Yeah, I just want to know if we are yeah, I'm just wondering what is the setting here. You guys should have more details on the setting. Yeah, because basically, I think something that you guys didn't think is that you can normalize the range, right? So whenever you have these numbers, you can always, you have a largest value, largest positive value, and a largest negative value. And what you can do is that you can compress the representation to be always between -1 and +1. So that when you do the numerical experiments, you can take sum of numbers that average to 0 and product of numbers that average to 1, let's say. And then you can play around so that the comparison is more fair, right? Because if you show me something like this, in the back of my mind, I'm thinking, what is the numerical experiments that gives rise to this? Okay, so in the report, just put more details, please. Okay, go ahead. Next slide.
Okay. And next, we are going to talk about the alternative representation and advanced investigation. And the scenario is that we simulate machine learning scaling path by performing 16 consecutive multiplication, and we compare it with meaningful. We compare meaningful and LNS. And for meaningful, the error accumulates significantly as like every step requires mantissa rounding. But for LNS, the exponents are just sum, and so the error is only introduced during the final quantization. And the result is that LNS demonstrate vastly superior numerical stability for long chain multiplication tasks. But when it comes to the broader ranges, the saturation and clamping can dominate both the formats and the master core of LNS advantage.
Okay, very good.
And next is the
Sorry, do you have
custom
numbers to the previous one or no? Okay. Would have been nice to see some plots there. Like you could show the different multiplication, how it accumulates. Okay, go ahead.
Okay. So next is the custom ABIT representation.
Let's see.
And we call it PLS8. And our design concept is that we want to overcome the uniform resolution of the standard LNS by providing non-uniform precision distribution across the log domain. And we allocate like one sign bit to determine the positive or negative, and 3 bits to define the 8 distinct log segments, and 4-bit intra-segment to provide 16 linear quantization within each segment to balance the range and log.
So you
precision.
log them apart, and then you have uniform intervals in between the log intervals. Okay. Okay. Very good. Go ahead.
Yes. And when it comes to the multiplication, is simulated in the log domain, and it requires a segment boundary search, so it maintains high stability for our product. And the
complexity goes up. Yeah, the complexity goes up. Yeah. Go ahead.
And for the addition, this representation requires a non-linear reconstruction, some recompensation workflow, so it increasing the computational overhead. And for the zero representation, it just like payload 0 is reserved for the extra 0 value. And the performance and benchmark result is when we compare the PLSA with Miniflow, it can achieve higher resolution than a 4-bit Mantissa Miniflow in targeted intervals. And when we compare it with LNS, it avoids the severe clamping errors seen in the standard LNS, like at extreme values. And for the runtime, because of the segment lookup logic, it typically shows higher latency in the software simulation compared to simpler format.
Very good. Sure. Tell me you have some plots. You have some plots, right?
I don't think we plot here.
Come again.
I don't think we have plots on this part.
Wow. Did you implement this in code? This submission at least?
Yes.
Show me something then. Show me some code or show me something.
Show you the code or
yeah, show me the code of the addition at least.
Okay. So here.
This comparison table. No, show me how you do the summation. Okay. This is the comparison part. Okay. X plus Y. I see. So you don't actually implement. I see. So you don't actually implement the addition. What you do is that the exact add. Just let me see this, right? PLSA add array float MD zip XY. I see. Okay, and then what do you do? Stay there. Add float PLS. Can you show me this function PLS8 add? Can you show me the function?
PLS8 add. Right.
Okay, there. Stay there. PLS8 the command set the code. Return PLSA8 encode XQ. I see. So you see why this is uninteresting, right? Can you tell me why this PLSA add it's uninteresting?
It's what?
It's uninteresting. You understand what I mean?
No.
Can somebody tell me why this is unsatisfactory for me? It's an uninteresting function. Can somebody tell me? Because here, right, you see that you take the number X and number Y, right?
Yes.
So whatever these numbers are, first you project them into the representation. So you find the closest point to your representation, and then you sum them together, and then you project them again on the representation. So in reality, this will not be interesting, right? This is like when you go and implement the algorithm, you don't want to do this in binary logic, right? So for example, when you do the summation in binary logic, right, you will do the XOR, you will do the summation of the exponent, so you know which binary logic you will use to sum the exponent, and then when you do the you have to sum out the mantissa, and so it's a very efficient binary logic algorithm. But here it's a little bit. Can you look at this PLS8 encode and decode? Go to those functions. You see what happens. Yeah, see here. So you can imagine that doing this operation in binary logic will be very complicated, right? Because yeah. So, yeah. You understand my point, or?
Because it encode and decode like too much times.
Yeah, so it's like this, right? So you have your two numbers, right? And they're in this representation. You sum them together in a 16 bits representation, and then you project them back again in an 8-bit representation. Okay? Is this clear?
Okay.
But then it's like if you had to do this for each operation, it would be very slow, right? If you, for example, if you do it for mantissa exponent, then you know that you will have to sum two numbers. Then you take the largest exponent, then you convert the number with the lowest exponent into higher exponent. So you put some zero in front. Then you do the summation of the mantissa together, and then you truncate the mantissa. Okay, so it's very clear to you when you sum two numbers what is the numerical operation that brings you to the loss of precision. Here is just it's obfuscated by this high complexity application. Okay, very good.
So
okay, very nice.
So is this like good for accuracy but bad for the runtime, or no? Okay, understand.
Correct. So it's sort of mask the runtime complexity. Yeah. Can we go back to the experiment? Let's see, because there were some numbers. Can you go back to the experiment, to the results of the experiments?
Here.
Okay, so this is representation, mean, max, and then the ratio, relative error, average error, and this is the 25 multiplications, right?
Yeah. Yes.
So can you tell me how you pick the numbers? Let's see how you pick the numbers. You said you do 25 multiplication, right? Can you go up? Show me. Yeah, stay there. Choose 1, 2, 3. Okay, so you choose 4 and 3. Then choose the dynamic range. Then error benchmark. Random default. Random number between 20 and 40. Number pairs final. I see. So you take the x and the y in terms of the range that you have chosen, right? You take 2000 numbers and you repeat, so you can do the float. That's nice.
Okay.
Yeah, so go to the table now. Go to the table now. Understand how that's normalized. And so then you have the mini float for 3, the LNS, and then you custom. And you do the max error, the minimum error, the relative error. I see. Average relative error for the multiplication for the addition. And the average relative error, so it's the average between the summation and the addition. Very good. Okay, understood.
Okay.
So this is also normalized. It's also normalizing the range. Yeah. Okay, very good. What was the question?
No. I think this is the end of our presentation.
Okay, very good. Yeah, just of course, you see, right? So that like if you let the machine write your code, then your understanding is very little, right? So it's, remember that you do this for yourself, not for me, right? So if you let the Gemini write all the code and you don't understand anything, then it's an opportunity lost for you, right? It's not too good for you. And then just put more details, right? Because it's clear that if you just present the plot, then somebody wonders how you got to the plot. So yeah, just put more details next time. Okay, very good.
Okay.
Let's go to the next group, Group D.
Okay, it's my turn. Wait.
Wait a second, let me write my notes. Two little details. Partially send the code. More simulation results. Okay, very good. Group D, go ahead.
Here is my presentation, and here's the level 1 challenge 0.
Sorry, but you guys have 4 people, right? In the group, you guys have 4.
Just 3 now.
Okay.
Start with the introduction of mini float. We only got 8 bits, so
just a second. Let
we
me
need
parse.
to what?
I said, let me parse. So the 3 groups before are 3 people. This group another 3 people. So 1, 2, 3. 1, 2, 3. Okay, perfect. Okay, go ahead. Everybody's here. Go ahead.
So we need to allocate a bit, and 1 bit is for sign. If s is equal to 0, the number represent is positive. If s is equal to -1, equal to 1, the number represent is negative, and the rest of 7 bits is allocated for exponent and mantissa. And in the challenge 0, we need to do 3 combination. Is 2, 5, 3, 4, and 4, 3. And we got this formula, and we need to calculate bias first. Here is the bias formula. So we take exponent and mantissa as 2, 5 to calculate for example. For e equal to 2, bias is equal to 1. So we only got 2-bit exponent, so we can only represent 0 to 3. And we put the number in this formula, we can get the smallest number is 0.5, and the largest number is 7.875. Okay.
Very good.
And I put several numbers in this range, in 0.5 to 7.875 to get this number. You will see the relative error is quite low. Average is 0.8%. But let's look at the image. If you
go back one slide, can you go back one slide? Next time, can you put them? No, next slide. Can you put them in order next time, please? Because can you put them in order from the largest to the smallest, please? Go ahead.
Okay.
It's just confusing for me. I was looking at the logic of the numbers. It's like, oh, why did he put one number after the other? It was just random, so confusing. Okay. Go ahead.
Okay. If you see this picture, you can see the green bar here. This is the range we got 0.5 to 7.875. In this range, the relative error is quite low, but if you out of this range, the relative error will start to grow. And we put 3 combination of exponent and mantissa together, we will see that exponent, if exponent is small and mantissa is big, you will see the range he can represent is small. And in the other hand, if your exponent is high, mantissa is low, your number represent is quite big, but the relative error will be a little high. So let's go.
Can you go back one slide? Can you go back one slide? Very good. So this is here you have the relative error that grows, and it's because you're in log scale. Okay, show me the next slide. And this is absolute scale. There is also log scale. So why isn't the relative error growing linearly, like in the previous one? You see here that the relative error is growing for negative exponents. But if you go to the next slide, then it's not growing.
Yep.
I
think there is some error here.
Yeah.
Okay. Okay, we go to the conclusion. We only got 8 bits, so the resources is very little. So if you want to calculate detailed data, you choose exponent equal to 2, mantissa equal to 5. But if you want to deal with the value with large range, choose exponent equal to 4, mantissa equal to 3. So we need to trade off between range and accuracy. And I got the plot here. You can see the bias and the minimum number and largest number. Accuracy is the minimum gap.
This is the minimum gap. Okay, very good.
Yep.
And you give me the minimum gap also as a ratio. Okay. Okay, got it. As a ratio. Yeah. Go ahead.
Okay. That's the end of level 1. Let's go to the level 2 for Philip.
Okay, so I will talk about level 2. So let me set up the slides myself real quick. Okay. So the first task in level 2 was the summation of many terms and then looking at how that affects the error based on the amount and loss of precision. Okay. So we took numbers from, I believe it was -1 million up to 1 million.
Okay.
Actually, no. Maybe it was from 0 with as small as like 1 millionth, so like 10 to the power of -6.
10 minus 6, okay.
Up to 10 to the power of 6. And you can see that the absolute error is pretty big for all the methods, like the naive, the Kahn, and the pairwise.
So pairwise, let me ask you really, pairwise means that you sum them all pairwise and then you sum them all together. How is the pairwise? So do you store the intermediate process? Yeah.
Recursively. So pretty much we keep splitting the array in halves until it's just two things, then we sum them, and then we sum the result, and then we sum the results of the result.
Okay, so this consumes more memory, of course, because you have to store the intermediate results. Yeah. Okay, very good.
Right, yeah, but it's only like logarithmic, no? Yeah, it does use more memory, that's true. So actually when n is 10, the pairwise is pretty much the same as the naive. You can see in the bottom left of the graph. But then as n increases to 1,000, pairwise is actually even the best in the end. It's even slightly better than Kahn. But for the smaller number of terms, Kahn is best. But we can see that even Kahan is not that good because still the precision is small for the amount of bits that we have.
Let me parse this. What you're saying is that the relative error decreases as the number of terms increases.
Yes, actually, that seems to be the case. So it might be because the relative error is relative to the number, right? And with
That is
amount
clear.
of
What is
items.
happening is clear, right? Both the numerator and the denominator are growing, right? And
Yeah,
you're
yeah,
saying that
exactly.
the numerator grows faster. Yeah, I mean, I guess if you choose your numbers, yeah, I guess. So these results are averaged over multiple runs, right? It's not only one run, right?
This is, I think, 100 runs. Yeah, when it was just one run, it was more random, but over the amount of runs, it was always like this. Like if I rerun it, it's going to be the exact same graph, so it's not variable.
Nice. Yeah, I think it will be hard to reproduce this result if you generate your random numbers with a different distribution, right? There is something that goes to zero, something that averages out toward like the numbers. You know what I mean, right? So if you sum all your random numbers, let's say, the sum of the random numbers will go to let's say 100, right? And so no matter how many numbers you add, you will converge to this constant value. So actually there is you lose variance in the code of sum as the number grows. But I don't understand what happened to your errors, because your error is also accumulating and maybe goes to another sum. Yeah, it's interesting. Good. It's a good point.
Maybe it's also because I think I used for comparison the numbers represented in the 8 bits. So it might be also that like the ground true that I'm comparing to is also like suffering from the loss of precision due to it being 8 bits.
This is it. That's the answer. That is the answer. That is the answer. I think that's the answer. Yeah. Correct. So I understand. So what you said is this, right? That when you look at the ground truth is also represented as 8 bits. So it's not represented as 16. Right.
Yeah.
It's a good point. That's what happens.
So yeah, here's the note. The error just grows with n, that's expected. Again, turns out to be the best, which is also expected. And that for pairwise to have an advantage, you need a bigger n, otherwise the gains are not very big.
That also makes sense because you're consuming a lot of memory, right? So the more n, the more you're using your memory to store the intermediate results and you lose less precision. Yeah? Go ahead.
Yeah. For the multiplication, we got results where you could see quite well the differences in the different split between the exponent and the mantissa. So the higher the exponent, the lower the error. In this case, like using 5 bits for the exponent was best, which only leaves 2 bits for mantissa, which is quite extreme, but yeah, it led to the best result because it also, like what you can see on the underflow chart on the right, that was probably the biggest thing. Like if you have more space for the exponent, it's not gonna underflow, and it's gonna have the biggest impact on the result.
Okay, so the underflow rate is in percentage. Okay, good. And
yeah,
this is summation of 20 numbers.
Yes.
And remind me, how are the numbers generated again? You said the numbers are random between?
It was -3 to +3, like logarithmic. Yeah.
Because your range was that.
So yeah, underflow was almost 40% for the exponent 3 and mantissa 4. So yeah, still scales with n, which is still expected. Yeah, our exponent seems to be better. Overflow actually never happened. It was only underflow during our experiments with quite a high range. And yeah, the underflow follows pretty much the same pattern as the error. Just the one difference is in the when we only have 5 numbers, right? With the exponent being 4 and exponent being 5, which is probably just that the size of the mantissa is significant still with that amount of numbers.
Yeah. Very nice.
Right. And then for the log sum, we saw massive differences between the naive implementation and the stable one. You can see that for the naive implementation, the error, I think it was almost like 0.7 when the vector had 50 numbers. And the stable one is, so this is logarithmic scale, right? So this the stable one was around 2%. So yeah, that was a big difference. And the failure rate, actually, we didn't observe any failure.
So failure is here when you go over the range. Okay. So here stable means that you do the max of the exponents, right? Is that what you mean stable?
Yeah.
Here?
Just like the task asks
Yep.
to do the maximum, like this minus the maximum.
Correct.
So yeah, this was probably like the biggest like effect that we saw in the experiments, like compared to, for example, the summation, the difference wasn't that big if you used Kahan or pairwise, but here it was like day and night with the naive owing that. Yes, and then finally for the order of operations, I'm not sure if there's too much to say about that, but yes, we observed that with these little bits, the order of operations matters, and you can get different results based on the order in which you do the operation. Because if you do the operation with a big number and a small number, it does nothing. If you do it the other way around, it does something. So yes, that's it for level 2.
Okay. Let's see for level 3.
Okay, so I'm going on level 3.
Very good. Upright, exactly.
Yeah, so we have really explored the absolute limits of an 8-bit mini float. As we see that from this like Beth tube curve, and then we know that designing a floating point system is like a zero-sum game. If we allocate more bits to the exponent, and we'll get a wider dynamic range, but sacrifice precision. And if we give more bits to the mantis, precision improves, but range shrinks. So we're looking to the L and S. The core idea of L and S is quite smart because we completely throw away the mantis. Instead, use 5 bits to store just the sign of a number.
Yep.
And a 7-bit fixed point represent of its base to logarithm, which shows as z. And because multiplying two numbers is mathematically equal to adding their logarithm. So this means that at the hardware level, we don't need a complex power-hungry multiplier circuit anymore.
It's so you know. I see. Yeah. So
Okay,
you know hardware. Yeah. Was this sentence informed by your experience, or?
So instead, we can perform real number multiplication using a very cheap, fast, and integer adder. But
very quick.
in engineering, there's no free lunch. Like LNS makes multiplication elegant, but it turns addition into a hard work. Because if we want to add two numbers in LNS, we have to calculate number in the logarithm domain, like it shows here. So then I see the multiplication show down, it shows a traditional mini float against LNS in a multiplication showdowns. The results are that while LNS introduced a small quantization error during the initial encoding, because we are forcing the logarithm into a fixed point grid. This error does not explode during multiplication, because LNS multiplication is just integer addition. It's exact at the hardware level.
Right.
But I've saw that some the column of arrow, there's some LNS have a bigger arrow than mini float, and I think this because that we choose a number randomly, and if the number is not closer to an index of 2, and it'll be like far from the grid points of LNS, so it'll be a larger arrow for LNS.
Correct.
So in machine learning, or like in deep neural network, we constantly calculate massive chains of probability or attention score. So in this case, LNS can provide incredibly stable continuous product with a fraction of the hardware cost and power consumption. So this is exactly why modern AI hardware accelerators are using LNS design.
See, I see that you did your homework, yeah. Do you want to tell the others what is an attention score? Just so that you give them some context.
So I'll just keep going.
No, tell the others what is an attention score.
Attention score.
You just mentioned attention score, right? Explain that to the others that maybe don't know what is an attention score.
What? Which attention score?
You said attention score. I know what you meant,
yeah.
But can you explain to others what is the attention score?
I don't really know how to
So why did you say attention score if you don't know what the attention score is? Right? So because one of the architectures that has been very successful in the last 5 to 6 years has been attention networks. So let's say that you have an image, right? And you're doing image classification. So there are you can train a network, right, to tell you which elements of the image you should look at in order to see if there is a cut in the image, right? And so, for example, a certain network will give a score to each pixel in an image, and it will tell you, oh, this pixel contributes this much to the classification of a cat in a picture. Right? So you can imagine that in an attention network there is a query, and there is a hit, and then you get a score. So the query would be, oh, is this a cat? And then the image goes in, and the network spits out a probability, let's say a heat map, probability that a certain pixel is correlated with your detection. Okay, and these are called attention networks. And attention networks, they are great. They do a beautiful job, but they have this issue that they have very high dimensions, right? So since they have to output a score for each pixel, right? It means that if you have thousands of pictures, then you need 1,000 of outputs of the network. So attention networks, they consume a lot of computational resources, and so that's why And what the network learns is learning to do basically a vector times matrix multiplication. And this is why this type of LNS is very convenient, because you have all the pairwise product between the matrix and the vector in order to output something. And so that's why having an accelerator that does this matrix times vector multiplication is very, very efficient. And of course, this goes down to this precision. Okay, go ahead.
Okay. So we go on. I choose a custom base experiment, like just easily choose like based in scientific notation format, and
Okay.
it's
Okay.
just to push the boundary even further. So just using 3 bits for the base 10 exponent and 4 bits for n is a mantis of an integer, and it can represent numbers up to 150,000, but however the average relative error is not very good.
No, but you're not being fair, right? Because all the other representation, they have 8 bits, and your representation is 4. Why didn't you take the same number of bits?
Oh yes.
Or shouldn't you
I
want
think
to compare it with the same number of bits? It's like comparing a bicycle with a car, right? It's like, oh, the bicycle car was faster than a bicycle, right? Where is that? Does make sense? Yeah. Anyway, go ahead.
I think I should
You understand what I mean? It's not a
choose
fair
the
point.
same mantis. Yeah.
And so just an unsigned integer notation. Yeah.
Very
lazy. Okay, go ahead.
It's also like this design highlight exactly what particle number systems are so hard to build in base 2, because in base 2 standard flows, normalizing a number is just a bit shift, but which is basically free in hardware, but in base 10 system, even mantis overflows during multiplication. Normalizing it requires dividing by 10, and
Correct.
Hardware divider circuit is huge and and slow, making this design totally impractical for real silicon.
That's a good point.
Yeah. And so like choosing these it can't easily say which one is better. I think it depends entirely on the workload. If you need a general purpose CPU balancing addition and multiplication, I think mini float is still the best compromise. But if are building an AI accelerator or for probability multiplication or something, NS is I think is the best. And just to conclude, this project I think taught us that there are many methods, and in different conditions we can just choose the most suitable one to solve the problem. Yes, so that's it.
Very good. Okay. I think we have 6 people in the class, so let me take my notes on group D. Did you guys work together or did you guys work separately? Because it feels like you guys work separately, correct?
Yeah, we have.
We worked together, but then we split the presentation.
Okay, good.
We split the presentation.
Yes. You guys work together. And how did you choose who will do which part?
Pretty much, somebody said I can do this, somebody said I can do that.
Did you guys share the code in between? Was there somebody that brought the code and then the other body prepared the presentation? Did you all share the code? How did it go?
Yeah, we all shared the code, and then just for the presentation part, we dove deeper to have it like prepared for the presentation each for our part.
Presentation was missing context. Context and some moment. Okay, very good. Okay, so I think I hope you guys understood what is the goal of the class through this first challenge, right? Because of course, as I said, you can so a little bit more philosophically, right? You guys are students, and when you're gonna go to work, you're gonna have these Gen AI tools at your disposal. So it's a strong temptation for you guys to just copy and paste into Gemini and get the presentation, get the results, get the numerical thing. But of course, you know, if you can do this, then everybody else also can do this, right? So it's very difficult as a student to know what to do, right? And to understand how to learn, because you have to learn to use the tools, but you don't have to follow into the temptation of letting the tools do your job. Because if the tools do your job, then you're never going to become better than the tools, okay? So we don't know how the world will be in 3-4 years, but basically the Gen AI tools are here, right? When you start over any topic which is new to you, you are down here. So if you keep using the tool and you just give as an output what the tool gives you as an output, it will going to remain here and the tool is going to remain there. What you need to do is to climb over the capabilities of the tool, okay? And it's a temptation. I mean, it is very hard to accomplish this when the tool gives you an answer in 2 seconds, and for you to understand the code will take 2 hours. So in my opinion, right, the difficulty for you guys as a student is to force yourself to spend the time to accomplish a task that you do not need to accomplish because the tool already does the job, okay? Of course, I can tell you that this is what you should do, because in my opinion, this is the best way in which you can be useful to yourself and to others. But this is a challenge that you guys have to face that nobody else had to face before you. So you shouldn't look out at anybody for suggestions and recommendations apart from what you think is going to be useful for you. I just would like to convey to you that this is why I structure the class in the way I structure it, so that you have the opportunity to understand what are the limits of these Gen AI tools. And also, it seems that the class is 6 people, okay, which is fantastic, right? Because you guys get to sit down with each other for the next whatever 10 weeks, and you can really focus on interacting with each other and working with each other. Which I think also you can interact with me, which I hope it's useful for you guys. So I really hope that that this was a moment for you guys to think and to realize also what is my perspective on the results that the AI tool produces and how much you contribute to them. It's very easy for me to understand what comes from you, what comes from the AI tool. Keep thinking about, if I had to give you a suggestion, keep thinking that you have to fight to become better than the tool. So you have to remember that Gen AI is a tool and you're in charge of your own learning, and nobody can do that for you. Okay, I didn't want to be too philosophical, guys, but yeah, I think this is, hopefully I don't have to say this any more time, right? So you do this for yourselves. So this is your learning experience. You're going to get a grade for this class, but I don't think it's relevant to anybody in 2026, knowing how the job market is going to be. So if you have any questions, ask me. Any questions? Otherwise, I'm very happy that we have 6 enthusiastic students who attend the class. Numbers are not important for me. 6 students is better than 100 because I get to talk to you guys more often. Otherwise, we take a break now. We walk around, we drink some water, we come back, we do the material that we need for the next challenge. I'm going to release on Friday, which is going to be on K-means clustering, which again, we saw in the introductory class, and then we move on from there, okay? I'll see you guys back at 33, 34, okay? See you back at 33, 34. Okay, if you have any questions, let me know. And then Naufal will open the E3 submission for your report. take care of the changes that we discussed during the presentation, and then you receive the form to do the evaluation of the other group. Okay, see you back in 4 minutes. Okay, guys. So, any questions? Let me know. So I'll just give you a reminder of what we did last time, and then we move on to the new materials. Vector purposes and norms. Okay, so last time we were doing this beautiful thing with Yeah, sorry, I don't know why I have to restart the system. My Chrome, my Adobe window is not sharing. I have to share the whole video, the whole screen, so you're gonna see a little bit of infinity window here. Okay, so remember that last time we were looking at vectors, right? So we describe what happened with vectors, we represent them. We said that we can represent the signals with vectors, we can represent images with vectors, we can represent words with vectors. Everything is a vector if you listen to me. Then we describe a data set, right, where we have different features in the data set. Then we went through, well, these vector operations, I think they're pretty neat. Then we did the inner product. We described what is the role of the inner product. Some examples of inner product, some use of this special vector EIs, which are the the basis vectors. Then we describe weighted sum. How can we describe whatever as a product? And there was this example on the portfolio return. Then we describe linear functions. I think they're very easy. Inner product is a linear function. Yeah, so this was the example with the initial mass, but this is all easy stuff. Then we describe affine functions, right? So the affine functions are the one in which the sum of the coefficients goes to 1. And then the Taylor approximation, we say first Taylor approximation is a differentiation of a function around a certain point z. This is a generalization of the Taylor expansion as you see it in usual courses, because here we take the partial derivative with respect to each entry of the vectors. And now we introduce this nabla notation, right? So this nabla notation is a derivative of a function, okay? And that takes an input over size n and outputs a scalar, okay? And if you take this nabla operator takes the function, it takes the derivative of the function with respect to all of the independent variables, okay? And notice that usually this x, so engineers and statisticians, okay? I speak as an engineer. So usually this z will be a column vector, and this nabla accordingly will be a row vector, okay? So this is very important when you start using these things in, let's say, in Python, because you have to remember the order of operations, right? So if you take a nabla of a vector, of a column vector, you're going to get a row vector, okay? If you take a nabla of a row vector, then you're going to get a column vector as its gradient, okay? So this nabla operator will be called the gradient. Very good. Then why can I not move? Then, in one variable, this what's going on with this AI assistant? Okay, so in one variable, this is as we said, that this is the meaning of an hyperplane that touches the function only in one point. And when you go into dimension, then you can think of this as, let's say, a hyperplane that touches the function only in one point, right? And it's supporting the function. I don't know what is this AI assistant. Sorry, guys. This AI assistant is driving me crazy. So what we want to do often is to have a regression model. We discussed this already in the introduction. And the idea of a regression model is that we're going to have a predicted label variable, which is a linear function of the feature vector x. Okay, so as we discussed already in the first lecture, these x values, we will call them as regressive independent variable or inputs, and y will be our intercept, our predicted variable, our dependent variable. And the job that we will often have is that somebody gives us a data set, and we have to decide what is the best set of values b, with which we can produce an estimate y hat, which is close to the true value. Okay, and we have to measure this loss, and usually we take an L2 loss to do this. Okay, so we did this example in which we have different houses. They have the bets. We do a prediction of the price of the house given the bets. So remember this one here. And then we said, well, we can do also complex variables. If we do complex variables, what we do is that we gain this dual representation in the polar domain, right? So you can also represent the elements in the vector as amplitude plus angle, and this is usually convenient in some specific application, right? So for example, when you talk about word embeddings, usually people train word embedding to represent semantic similarity on the angular domain. Very good. Complex vector, we said that don't worry about it too much, and then remember that you only have to switch from the transpose to this Hermitian transpose. So what you do is that you conjugate the part of the complex part of a vector, and if you do this, let's say the usual rules of the inner product, they remain the same. Very good. Okay, so now we talk about. Oh, damn it. Any questions about this part, guys? So we're following these notes here, right? So this is the UCLA professor that I like, and we're following these slides for this one here. Okay, so we did the vectors. Now we're going to do the norms. Okay, and this one here is going to bring us to the topic of the next challenge, which is going to be the k-means. So let's move to that one there. I'll try to fix my computer next time, guys. It's kind of annoying. Okay, good. So when we talk about norms, we have an idea of calculating the magnitude of something, and the norm that you guys all know is this Euclidean norm, right? Somebody gives you a vector A in Rn, and what you do is that you take the square of each of the elements, and then you take the square root. And now you understand how you can write this as the inner product of the vector A with itself. And then you take the square root. And note that if n is equal to 1, then you have the absolute value. And sometimes we use this notation because the Euclidean norm can be generalized to any other power, right? So here you can put power 1, power 2, power 3. And well, the square root can be square root of 1, square root of basis 1, 2, or 3. So usually we use this double bracket, this double column notation, I don't know, guys, this double thing notation to indicate the norm, and then this little number and the suffix will be indicating the norm, right? So if we write the L1 norm, we will call this L1 norm. This is the sum of the absolute values, and we're going to see some of these norms later on. So in this AI tool is bothering me. Let's see if I go in full screen. Let's see if it gets better. Sorry, guys, it's because Adobe have been trying to put AI tools everywhere, and it's not integrated very well. Okay, good. In general, it is more convenient for us to generalize the notion of norm from the L2 case to any other way in which we want to define the magnitude of something. And so what we can do is that we can define a set of properties that we want this generic norm concept to have, and then we can try to define norms that are useful for us in different contexts. And what are the properties that we like? So we said that we want positive definedness. So the only vector that has norm 0 is the 0 vector. Homogeneity, right? If you multiply by a constant, this constant comes out in absolute value from the norm. Triangular inequality. This is what it's very intuitive for us into the Euclidean case, and the block properties, right? So if you have if you have a matrix, then you can chop down the matrix into sub-blocks, and then this formula works. Something that we always use is the Cauchy-Schwarz inequality. I think you guys already saw it at some point in your life, but this is the inequality. And notice that this property is solved, right? So it's 0 only if one of them is 0. Okay, the proof is here. We're not going to go through the proof. Fairly easy. Then we discussed last time the difference between average and RMS. Okay, triangular inequality from the Cauchy-Schwarz. And then we get to the notion of distance. Okay, so the distance is the norm of the difference vector. So if somebody gives us a vector A and a vector B, then we will define the distance as the norm of the difference between the two vectors. Okay, so these tools tell you how to go from a distance to the norm. And there is also a trick in which you can turn a distance into a norm. Okay? So here you define the distance as a function of the norm. There is also a way you define a no norm as a function of the distance. So the norm, again, if you want to, the distance, if you want to define a distance in a more general way, you would have to say that the distance is always positive, and the distance is equal to 0 only if the difference vector is equal to 0, and the distance has to satisfy a triangular inequality. Okay, so this is, again, familiar to you guys. And notice that the RMS, the root mean square, is the deviation between two vectors, will be the norm of the difference vector, so the distance between the two vectors divided by the square root of the dimension, so that it's a dimension-free. We will call this as a dimension-free measure, right? Meaning that it is normalized by the dimension. Good. Then again, something that we saw last time. What is the average? What is the standard deviation? So you take a vector, you subtract its average, then from the you look at the root mean square of this zero mean vector, and this gives you the standard deviation. And then we are discussing this. Okay, this is good. This is good. This is another exercise that you can look at, and then we say that you have a collection of vectors. So when you have a collection of vectors, you can define the center of the collection of vectors, which is the average of all the vectors. And now we get to the K-means algorithm. Okay, now I'm going to slow down because this part is new. So this part is not new yet. Okay, so we said, remember that we have a set of points. We want to define a set of points, and so we do different clusters. We iterate between the clusters. We do this and that and that and that and that, and then we get to the final cluster. Then we said, oh, for the images, we have the CFAR10 image set, and we can recover the number by applying clustering. Okay, so I did a review here because I wanted to say that the next challenge is going to be on this algorithm. Okay, so this is an algorithm which is very, very common. It has a lot of numerical aspects. So the next challenge is going to be on K-means clustering. So I just wanted to review so that you guys know that it's coming. And this part, I think this part, it's okay. I think we can go to this. Okay, good. Okay, so let's just finish with this. Let's go with this part. Okay, so when you have vectors in any dimension, you can define the angle between two vectors in a dimension with the arccosine of what? The inner product between the two vectors divided by the magnitude. Okay, so this is generalization of the angle that you see in two dimension, and this is an idea of angle that it's in any dimension. Okay, so this is, remember that this is always a scalar. Okay, and so then given this means that if somebody gives you two vectors, you can always express their inner product as the product of the amplitudes times the cosine between the angles, the cosine between the vectors. And given the Cauchy-Schwarz inequality, we know the inner product is always less than the product of the magnitude. And so this value is always going to be between -1 and +1. And in fact, so be careful when you do this conversion that sometimes you forget what are the unit of measure of the arccosine. So remember, the arccosine will spit out a value between -1 and +1. And yeah, so just some terminology here. I'm sure that you're familiar with this. So if the angle is 0, then the two vectors are said to be parallel, and it means that the inner product is equal to the product of the magnitudes. Then if theta is less than pi/2, then we will call this as an acute angle. If theta is exactly equal to pi/2, then we have orthogonal. So this concept of orthogonality, of course, also holds in higher dimension. If theta is between pi/2 and pi, then it will be obtuse. And if theta is equal to pi, then it means that they are anti-aligned or opposed to each other. And this is the last case here. Very good. So if we remove the arc cosine from the definition of angle, then what we have is we have a correlation coefficient. So this correlation coefficient will still have a range between -1 and +1. And well, when we calculate this correlation coefficient, what we do is that we always d-mean the vectors A and the vector B. Okay, so if we have a vector of A, then we center it in the origin, so we remove the average of A from the vector. If we have the vector B, then we remove the average of the values B, and this is called d-meaning. Okay, so this is an operation that you do most times. So whenever you have data, what you do is that you generally standardize the data, meaning that you get the data to have zero mean and to have variance 1. So that in a sense, as we discussed before, right? So in a sense, you have all the data in your data set that use the same range of values that your float 16 is able to use efficiently, basically. Okay, so notice that the vectors that you cannot have zeros at the denominator. So you have a problem if the vectors have zero, they're all zero vectors, so not interesting. So if the vectors are constant, so the one vector multiplied by the constant, then this correlation coefficient does not hold. It's always between -1 and +1. And if you want the full expression is here, and you can think of it as, I don't know, the average probability deviation from the mean in the standard unit. Okay, so if you explode the formula, maybe this formula would make sense to you. Okay, so here we have a few examples of different data series, A and B, what the values of A and B are, and what the corresponding correlation coefficient between A and B is. So you see here that A and B are very close, right? That they have the same trend, let's say, so that the correlation is very high. Here they have an anti-trend, right? So if one rises, the other one falls, so the correlation is very close to -1. And here the two trends are not related, so what you have is an average value of 0. Okay, so it's fairly intuitive. And here you see the scatter plot in which you have the series represented not as a function of time, but as pairs, right? So in this case, we have the value of 1 of the sequence A, the value of 1 of the sequence B. This corresponds to a point in the plot. And basically, if you do the scatter plot of this pointwise representation of the sequences, you will see that a strong positive correlation, close to 1, will be a line with alpha equal to 1. If you have a strong negative correlation, then it will be a strong -1 pattern. And if the data is random, then there will just be like a randomly selected set of points without any particular correlation between each other. Okay, so this gives us the idea that we can try to represent, we can try to capture correlation in a geographical representation, in a geographical manner. So the idea, you take two vectors, vector A and vector B, and then you draw all the pair of points A of k and B of k, and then you try to take an affine function, you try to slide this set with the affine function, right? And this affine function will have coefficients C1 and C2, and then you would say, well, roughly, like the relationship between my point A and my point B will be this linear function of A that spits out something which is close to B. Very good. Again, we have to formalize this because this intuition is there, but it's not mathematically formulated. In which sense we want this line to pass through the scatter plot. So the idea is that we can set up a problem in which we minimize the difference between y hat and y, so between f of A of k and B of k. And what we want to say is that we want to minimize the L2 norm of the error, okay? So n will be the size of our data set. A of k will be the feature for the entry k. B of k will be the label for the kth element in the data set. And what we do is that we have chosen a model that produces an estimate of B, which we call B hat. And then the way in which we penalize the model producing f of a of k instead of b is by taking the norm square, and then we accumulate the norm square over all the elements in the data set. Okay, so now we want to figure out how to optimally choose the parameters C1 and C2 so that we minimize the loss. Okay, so the idea is as follows: we explore this constant, so we will have C1, C2 a of k minus b of k squared. Here everything goes nicely, right? We can explode the terms and then take the summation. So the C1 appears n times, the C2 square appears n times, and so on and so forth. And when you do this, you see that the average of A appears, the average of B appears, and then we have what are the cross terms? We have the AK times the BK, and this is the inner product. A transpose B transpose. Okay, so in a sense, we see that the mean of one vector appears, the mean of the other vector appears, and a correlation. Okay, so then we have to choose the minimum of this because we want to find the coefficient C1 and C2 to minimize this. So we take the partial derivative with respect to C1, we take the partial derivative with respect to C2, and then we set these two partial derivatives to 0. Okay, so if we set the partial derivative with respect to C1, we get this equation. And so if we set the partial derivative with respect to C1 to 0, we obtain this equality. Then we take the partial derivative with respect to C2, we set it to 0. And now we have two unknowns, which are C1 and C2, and we have two equations, which we need to send the gradient to 0, which are these two equations. So what we do, we know how to solve a system of two unknowns and two equations, and this gives us this expression, which is the expression that we already saw in the first week, which is the optimal solution to the regression, and this is the interpretation that we have. So C2 can be seen as a slope of the line, right? And the slope of the line is the correlation coefficient between A and B, multiplied by the standard deviation of B and divided by the standard deviation of A. Okay, so this is very much what you would remember from your high school when you have 2 points and you're finding the line of the points, the equation of the line passing through the points, right? So you have the difference, you know, y1 minus y2 divided by x1 minus x2, right? So this has the role of your y, and this is the role of your x. Okay, and then, as we already said in the first week, once we have figured out what the value of C2 is, then we choose C1 so that the average, right, the average value of B, the line crosses the average value of B for when x is equal to the average value of A. Okay, so this is the coefficient, and this is, if we set this to 0, then we get the value of so the constant coefficient C1. Okay, so this is it. This is telling you that at the average value of x, then your line is passing to the average value of B. Okay, very good. As we said, this is a very beautiful thing because it's a closed form solution that we don't expect to see in many other points in our life. And again, here we have different examples of different data sets. So these are different scatter plots, and this is how the optimal solution goes. And the idea here is to observe this aspect here, which is the one where there is no correlation between A and B, and you can ask yourself, well, what is the model doing here, right? Because the model is the model could be picking any line, right? So when I do my optimization, it seems that if I change the value of the coefficients of this line, right, there is not going to be much sensitivity to a big change in the slope of the line, okay? Because this is roughly a square, right? Roughly a circle, and this line that crosses to this circle could be crossing in any direction, and you know, and the result of the fitting will not be much affected. And so you have to ask yourself. I hope that you're asking yourself, when do we see this the sensitivity of the solution with respect to the zero correlation case? Okay. Then a little A little discussion on the complex vectors. Of course, everything goes through the same way. Cauchy-Schwarz inequality still works nicely, but we have the Hermitian. We have the this complex conjugate, and that's all right. Okay, good. Tell me if I'm going too fast. Hopefully not. Okay, no questions still. So we do a little bit more about matrices. Full screen mode. Okay. Again, I'll try to go a little bit quick. Let me know if I'm going too quick. I assume that most of these notions are already clear to you. So this is a matrix, right? It's just a two-dimensional vector. So we have rows and columns. Usually we indicate the row first and the columns later. Some people use curly brackets or square brackets. It's always the same. And we say Aij. We denote the element in position Aj in the matrix A. So matrices are usually capital letters. And the elements and the lowercase letter are used for scalars. Then also we use them for vectors. So a little bit of confusion in notation, but we don't have three different sizes of Roman letters. Disadvantage of this notation. So of course the scalar could be a 1 times 1 matrix. Yeah, but usually we don't distinguish this. And remember, with vectors, we have column vectors and row vectors. So in the matrix perspective, a row vector is 1 times n vector, and a column vector is n times 1 vector. And usually we describe matrices as we describe people, right? So if M is larger than n, then we say that the matrix is tall. If M is less than n, we say that the matrix is wide. Some people say fat. I guess I'm culpable of saying fat matrices, but of course we don't want to discriminate with people. You can be wide and be whatever body shape you want. And if M is equal to n, then we just say that the matrix is square, okay? It's very useful to describe block matrices, right? So you can say that a matrix A is composed by this matrices B, C, D, and E. And you see that you can define the B to be a certain vector, the B to be another matrix, the D to be a scalar, the E to be a vector. So basically, you just have to make sure that dimensions are compatible, and then this type of block matrix notation is very convenient when you want to describe some operation involving large set of elements, right? Now, what sometimes we want to do is that we want to extract specific rows or columns from a matrix. And usually if we want to extract rows, we will use this notation, okay? A1, A2, and N. And if you want to extract vectors, then you will use B1, B2, Bm notation, okay? So this notation is not fully unequivocal. So sometimes we will use a different notation. We could use like a Python-like notation where we have a column, comma, the row number, but we'll discuss that when the necessity arises. Of course, we have our special cases, the matrix of all zeros, and then the identity matrix, which is the matrix that has all ones on the diagonal, which you can see as a stacking, either column-wise or row-wise of the unit vectors E. Then symmetric matrices are what you expect. The elements in position ij is equal to the element in position ji. And then the Hermitian matrix is a matrix in which the elements in position ij is a complex conjugate of the position of the elements in position ji. Diagonal matrices, they only have elements that are non-zero along the diagonal. Lower triangular, upper triangular, they are the matrices that you expect. And now something nice, right, that you probably haven't encountered before, but which is very, very important for us, is the idea of a sparse matrix. Okay, a sparse matrix is a matrix in which most of the elements are zero. And you will ask yourself, why do we have this special discussion about sparse matrices? the more we live, the more sparse matrices we see in the real life. So if you want to store something, often cases you observe sparse matrices. So for example, imagine that you have a database, right, where on one axis you have the users, the other axis you have the movies. This is the classic IMDb dataset case. Of course, the number of movies are comparable to the number of people, okay, on a certain website. But of course, a certain person can only see a few tens of movies, and even in the extreme cases, you have somebody that can watch at most 10,000, I don't know, 1,000 movies, right? You cannot have a person living today that has seen, let's say, 90% of the movies that have ever been produced, of course. And so it's clear that in this situation, the matrix that we want to store is the matrix that says which ranking a certain person gave to a certain movie. And for each row corresponding to each row of the matrix, we can have at most 1,000 elements which are non-zero over millions of columns. Okay. And if you realize that the data that you want to deal with is naturally sparse, then you can design a lot of very beautiful algorithms that are able to exploit the sparsity of the data. Very good. Let's go on very smoothly for today. So scalar matrix multiplication, I don't need to discuss it with you. Addition, I don't need to discuss it with you. Transposition is when you flip the elements on the columns with elements. You flip the elements around the diagonal. No need to discuss it further. Conjugate transpose is when you change the sign of the complex part. Matrix times matrix product, no problem. And now something nice, okay? So let's say that somebody gives you a graph, okay? So let's say that this graph represents, for example, the transportation network in a certain road, okay? So these are five places in Shinju, okay? So let's say that this is the train station, this is Jada, this is Chinda, this is Naliao, and I forgot, okay. This is another place in Shinju, and you want to say, okay, so this road is a one-way road, this is a one-way road, this is a one-way road, and then here we have this road here, and this is a two-way road. And you can ask yourself, how can I represent, let's say, the path that I have to take to go from, let's say, from 1 to 3, okay? Because it's clear that I don't have a direct path, so I have to choose a certain path along the graph. So you can ask yourself, well, this operation, how can I code it? How can I do it? Is there an efficient way of representing the operation that I'm trying to do? And of course, since this is an example, the answer is going to be very nice and clean. So what you do is that you use a matrix representation in which you have a number of columns, a number of rows, which is equal to the number of nodes that you have in the network. And then you go and you put a small one if there is an edge that goes from the elements j to the element I. So you see here, for example, this is 1 to 2. So there is an edge from 1 to 2. And this is 1 to 5. This is the element 1, 5. So it means that there is an edge between 5 and 1. And this corresponds to this edge between 5 and 1. And notice that we have an edge 1 to 2 and 2 to 1. And so this corresponds to the fact that this element is symmetric. Okay? And then the question is, if I want to go from, we said that node 1 to node 3, how would I do that? Okay, and the point is that if you take a matrix and you multiply the matrix by itself, this matrix will tell you how you can get to that point. For example, in this matrix, so this is the matrix A, let's call it incidence matrix. No, this is an adjacency matrix, sorry. This is an adjacency matrix. So if we take the adjacency matrix, we see that there is no 1. We said we want to go from 1 to 5, right? So from 1 to 5 will be the element 5, 1, 0, 0, here. Yeah, so there is no element here. There is no element in 5, 1. So I know that I cannot go in one step from 1 to 5. Then what do I say? I observe that if I take the matrix A square, right? The matrix A square corresponds to all the possible nodes that I can reach with 2 steps. And the cardinal, if there is a non-zero element, means that in 2 steps I can get to the node. And if I had a node which is value larger than 1, this will be an integer, and this integer means that I have 2 different ways of going from that node to that node. Okay, so you see that we are hair square. We have a 1 here, which means we can go from 1 to 5, and this would be from 1 to 4. Wait, how do we go 1 step? Okay, I go up. I go 1 to 4 and 4 to 5. Okay, so in 2 steps I'm there. And we notice here that we have a 2 when going from 5 to 2. Okay, we're going from 5 to 2. And we see that we can go from 5 to 1 and 1 to 2. And we can go from 5 to 3 and 3 to 2. Very good. It means that we have 2 ways. Then if we take the cube of this matrix, then we see, for example, that we have 2 possible ways, right, of going with 3 steps from 4 to 2. Okay, so in 2 steps, so 4 to 3, 3 to 2. But it's 3 step, guys. So no. Okay, 4 to 5, 5 to 1, 1 to 2, or 4 to 5, 5 to 3, 3 to 2. Okay, these are the only 2 ways in which you can go from 4 to 2. Okay, so the different matrix tells you if the element is 0, means that you cannot go from that node in that other node in this n number of steps, where n corresponds to the power. And if you have an element which is greater than 0, this is going to be an integer, and this corresponds to a cardinality of the number of ways in which you can go from a certain node to a certain other node. Very good. Something that you don't think about too much. So the matrix to matrix product is associative, so we can order the operation as we wish. It's associative with respect to the scalar multiplication. So if I have a constant and I have AB, I can multiply, I can plug this constant however I want in my multiplication. The matrix multiplication is commutative with the matrix sum. So if we have A times B plus C is equal to AB plus BC, if we have A plus B times C, this is AC plus BC. And then transposition as this property, right? But this is not commutative, okay? I think you have heard it many times. That A times B is not equal to B times A. It is more interesting to ask. It is more interesting to ask when this is true. Of course, you understand that one exception is when A is the identity matrix, so A times I is equal to I times A, and you can ask yourself in which case this is commutative. Okay, in which case AB is equal to BA, which is beyond this case. And yeah, it has something to do with eigenvalues, eigenvectors. We're going to get to it later on. Okay, so notion of linear product, so it's okay. And the matrix product with block matrices. So here we have 2 block matrices. You see that sort of the same structure as for matrix element appeals to blocks, right? So here, if there were scalar matrices, we'll have that the elements in this position will be AW plus BX, and you see this is exactly the same way in which you would do it as if you were a scalar, right? So everything is very nice and easy. Linear and affine functions. Of course, we have linear functions from vectors. Nothing says that you cannot have affine functions for matrices. So you see here that you multiply by a matrix by a vector. So you have that this x1 multiplies all the first elements plus this. Yeah, you understand. This is just a matrix times vector product. But if your x is an independent variable, then you have a function, right, that produces the vector y as a function of the vector x. So this is a function, let's say in general, m times n. Okay, so you map n input into n outputs. So a linear function, again, also applies to the definition of linear function, also apply to this function that output a vector instead of output a scalar. And then you can say that if you have an m times n vector, then you can see this as a linear function that brings you from Rn to Rm. And basically, from the mathematical perspective, right, what you say is that there is a function in which you apply element-wise, okay? And you can think that what you studied for functions that take a vector in input and produce a scalar in output are then applied element-wise to the output of the function f of x. Okay, so you see here that you see here that this is the interpretation of the function, and nothing rocks your world. Okay. So in general, we can think about this function f as an input-output operator. So we have an input of size n, which is equal to x, and this produces this function. It's a black box that we apply that produces an output m. And of course, this can be useful in many different interpretations. In particular, when we want to think about concatenating these blocks in different orders. So we can stack the two functions. We will say that we apply these two functions sequentially. Okay? So there is a sequence. So first comes A, then comes B. Some useful matrices. Again, something that's nice to know. So there is the identity matrix that preserves the order of the elements. And there is also the reversal matrix. So if instead of having the main diagonal equal to 1, you have the main anti-diagonal equal to 1, then you see that this has the effect of reordering the elements. And in general, right, so you can describe the permutation matrix as a matrix that has 1, 1 per column and 1, 1 per row. And this corresponds to a matrix that shuffles around the elements in the vector according to some order. And in particular, you have this circulant matrix, which is the one that shifts down all the elements in position from k equal to 2 to k equal to n minus 1. So you see that they're all shifted down. And the last element of the vector is put back on top. Okay, so you see here that this one here takes the last elements of the vector and puts it in the first position. And you can imagine that you can combine these operations, and if you can combine these matrices, then as if you take the product of these matrices, and since you only have zeros and ones, and you have 1 0 per row and 1 0 per column, then you will also apply, or you also obtain a binary matrix that has only 1 1 per row and 1 1 per column. Okay, and this is the permutation matrix that we're describing. The matrix tells you that in position 1 you will find the element 2, in position 2 you will find the element 4, in position 3 you will find the element 1, and in position 4 you will find the element 3, just as we expect. Rotation matrices, so we describe what a rotation is now in 2 dimensions. Okay, we can describe, we have a one-to-one correspondence between the correlation coefficient that we saw before and the rotation. Okay, so you only have one parameter theta, and you can construct a matrix cos theta minus sin theta cos theta, and this will have the effect of rotating the vector x into the vector ax. Very beautiful. Then you have reflectors. Okay, projections and reflectors. So here we have the vector x and the vector y. So what we are doing is as follows, right? So here we have the vector y, and we have the vector y is the projection of the vector x on the direction a. Okay, so this is the projection through a. So you see that this is the vector x, and we are projecting here, and this is y. And the equation of y is a transpose x divided the norm of a multiplied by a. So if you write this as ax, then the a will be a times a transpose divided by the norm of a. And then you have that z is the reflection of x around the vector, the direction a. Okay, so mathematically, right, if you geometrically, this will correspond by the vector x plus twice y minus x, the different x, because you see that this is x, this is y. Okay, so we are taking x minus y will give us this gray segment, and then if we double it, we have this other segment, and so z is equal to x plus 2y minus x, This corresponds to Bx, and this in matrix form takes the equation of 2 divided by norm of A times A transpose minus 1. Okay, so remember these formulas because they will become convenient for you at some point in life, hopefully. So let's go back to our graph example. So here we say that we have a directed graph with m vertices and n arcs. And before we had the adjacency matrix that told us which node was connected to which other node. Now we can also have the incidence matrix, which is a 1 if there is an arc that enters J, an arc J that enters node I, minus 1 if there is an arc J that leaves node I, and 0 otherwise. Okay, so in this case we have that on the rows we have the nodes, and on the J we have the arcs, we have the edges. So you see here that in the node 1, okay, we have that we receive this arc 4, okay, so we have a plus 4, and there are 2 arrows leaving, which is the arrow 1 and the arrow 2. Here we have minus 1, minus 2. Okay, so this is another way of representing an undirected a directed graph. We saw the adjacency matrix and the incidence matrix. And the current current law is just described in terms of this, right? Because you're saying that the total current arriving somewhere has to be equal to the total current leaving this part of the circuit. And so you are saying that this equation AX of I is equal to the current node, the total node arriving to I. And what you want to do is that you want to enforce this equation. You want to have that the sum of the positive voltage is equal to the sum of the negative voltage. And so this becomes this A transpose Y, which you express as follow, because the elements in position J of A transpose Y will tell you the negative voltages minus the positive voltages, and this has to be balanced. Okay, very good. Now convolution. I think you guys, I don't know, because you guys are bachelor, I don't know if you've seen convolution yet. When you do linear system theory, LTI, linear time invariant systems, then you will see this. Basically, if you see it in isolation like this, it looks a little bit weird, but we'll try to give it a meaning. So we have a vector n, and we have an n vector A and an m vector B. And the result of the convolution will be an m plus m minus 1 vector C, where basically we take the AI times Bj, where the distance between I and j is equal to k plus 1. So it looks a little bit strange, but bear with me. When you see it in the next slide as a representation, it will make more sense. So in this case, we take k equal to 1, okay? So we want that the I plus j has to be equal to 2, okay? So I plus j is equal to 2, if we only have 1, 1, okay? Because if we have to add 2 plus 1, 3 plus 1, whatever, 1 plus 2 in the indexes I and j, then this will be greater than 1. So it's only that one element. If we set k is equal to 2, then of course we have that I plus j has to be equal to 2 plus 1, which is equal to 3. So we have two elements. We have A1 and B2, and A2 plus B1, and we sum them together. Now let's say that the sum of the elements has to be equal to 3 plus 1, which is equal to 4. And now we have these three elements. We have 1 and 3, 2 and 2, and 3 and 1, and so on and so forth. Well, kind of strange. So why do we bother about convolution? Because if we have two polynomials, and they are polynomial A and polynomial B, and then you go and you look at the product of the polynomial, which is P of x times Q of x, the product of two polynomials is again a polynomial, okay? But the coefficients of the polynomial will correspond to the convolution, okay? And now you understand it, because, for example, if A1 has polynomial degree 0 and B1 has polynomial degree 0, So the C1 can only be the multiplication of the 2 degree 0. Okay. Now let's say that A2 is degree 1, B2 is degree 1. The only way to obtain in degree 1 will be 1 plus 0 and 0 plus 1. And this will tell you that C2 is equal to this, right? A1 B2 plus A2 B1, and so on and so forth. Very good. What are the properties of the convolution? It's symmetric. A convolve B is equal to B convolve A. Is associative because A convolve B convolve C is equal to A convolve B convolve C, and it's associative. And again, the only zero, right? The only zero element of the convolution is if you have an all zero vector. Okay, so if you have that A convolve B is equal to 0, then either A is equal to 0 or B is equal to 0, and this is a non-exclusive OR, right? Meaning that A is equal to 0, B is equal to 0, A is equal to 0, B is not equal to 0, B is equal to 0, A is not equal to 0, and A is equal to 0, and B is equal to 0. So this is non-exclusive OR. And this follows from the proper polynomial interpretation. So you'll have to believe me if I tell you that if you haven't taken signalizing systems, you have to believe me, but basically the convolution operator corresponds to some very natural operation. And for example, some very natural operation that generalizes concepts like smoothing or detecting edges or sharpening an image. So there are many useful operations that we can describe as convolution. The one that is easiest to explain will be, for example, if we choose A to be 1/3, 1/3, 1/3. So it's clear that the Y in position K will be equal to the average of the current element in the vector, the one before and the one after. So if we take a vector and we take this sort of local averages between the entries, then what you obtain is a smoothing out of the vector. And so you see that here you have a very jagged version of the vector, and then you put it in, and it becomes nice and smooth. Now, this operation of convolution, right, takes can be represented as a matrix multiplication. So we can either represent it as a matrix time vector, where A is the matrix, B is the vector, or where B is the matrix and A is the vector. And the idea is that there is this Toeplitz structure, and you see here that it's a banded diagonal matrix. And Toeplitz was an Italian mathematician, of course, as for your information. And you see that with this band matrix construction, if we take this big matrix A multiplied by B, this corresponds to the convolution operator. And so if we are interested in applying this convolution, for example, this convolution is a smoothing operator, and we want to implement it with an image, then it's clear that we can implement this multiplication as a circuit and fix this circuit and apply to all of the images. So it will make sense that this A gets fixed, and this B, you think of it as the independent variable, and this C is the dependent variable, and so you will construct this embedded matrix. Very good. We go a little bit, we go until here, okay? We're almost done, guys, we're almost done. So, okay, now we see a van der Monte matrix. So let's say that we have a degree of polynomial, a polynomial of degree n minus 1, it has the coefficient x. Then if we want to evaluate P of t for a certain set of point T1 to Tm, what you want to do is this, you will construct this matrix, right? 1 T1 all the way to T1 to the power of n, 1 T2 all the way to T2 to the n, and then you multiply it by x there. And then you will see that the polynomial evaluated at x is equal to a times x, okay? Very, very natural. I mean, it's very natural in the sense that you are flipping the role of the dependent and independent variable here. Usually we will think that the t is the dependent variable, but here the x is actually the independent variable. And this type of matrix is called the van der Monte matrix, okay? And basically the f of x equal to a of x maps the coefficient to a polynomial to a certain function value, okay? So now your input are the coefficients of the polynomial, and the t's are the points in which the coefficient is evaluated. And here comes a very useful function. Some of you might have seen it, some of you might not have seen it, which is the discrete Fourier transform, which is the van der Monde matrix constructed in this way. And the values omega that you see in this matrix, they have a certain power, right? You see that here they have a certain power, and the power here is it's a complex exponential, and the complex exponential is 2 pi j divided by n, where j is equal to the square root of -1 if it exists. Okay, so we don't know if complex numbers really exist or not. Maybe we just dreamed about it. So usually we say, oh, j is equal to square root of -1 if it exists. Otherwise, it's just the imaginary unit. Okay. So the DFT is a square matrix, and it has the effect. It's a van der Monde matrix with n equal to n. And it has the role of mapping the vector x1 to xn to the vector y1 to yn. Very good. Affine functions. Again, nothing that we haven't discussed before. This is like a linear function as we saw in the vector case, but the coefficients are sum up to 1. So just generalize things. Affine functions, we can apply them to the matrix time vector product. And we discussed before what happens when you take the derivative of a vector with respect to of a scalar function with respect to a vector of inputs. Here, finally, we have a vector to vector function, right? So this is a function that goes from n to m, and you can ask yourself what is the derivative of this object, because it's clear that you want to have a matrix in which on each row you have one of the elements of your output, so the f1, f2, f3, and in the columns you stack all the independent variables. Okay, so if you understood the nabla for the nabla operator for the function that takes a vector and output a scalar, then you apply this nabla operator element-wise to all the elements of your output vector, so that you obtain a matrix where the row iterates over the independent variable and the columns, they iterate over the components of the big F matrix. Okay, and now you have a notion of a derivative of you have a notion of a derivative of a function of m inputs and n outputs as taken over the inputs, right? So you're taking the derivative of the output of size n over an input of size m, and this is an n times m matrix. And when you studied it in high school, when you did the transformation of variable, this was the Jacobian matrix. But now that you grow up, you're engineers, you have a student ID from Jota, you can call this simply derivative. There is no need of having a specific name for this once you understand the generality of the operation. And f hat is a local affine approximation. Go ahead.
It's already 3:30 and I still have another class. Sorry.
Okay. Go ahead. But you're gonna have the
Sorry.
recording, right? Well, we're recording, so no worries.
Okay.
We're gonna be done in 5 minutes, yeah. But yeah, we also have the recording in 10 minutes. So ciao. We lost one student.
Ciao.
Yeah, just stay with me. We're almost done. So now we have this derivative, and then we do the complexity, the complex case. We can have complex matrices, complex functions, and that's it. Okay, very good, guys. I think we go ahead. Let me stop the recording. We say hi to the people in YouTube. See you guys later. Okay.